Back in 1994, this paper comes out from a researcher at AT&T Bell Labs. Now, it didn't exactly make the front page news, but hidden inside was, well, a blueprint, a key really, that could theoretically unlock almost every digital secret we have. So yeah, let's get into what makes this single document so incredibly important. I mean, seriously, what if just one paper held the key to everything? It sounds like something out of a movie, right? But that's the real question that Peter Shor's work forced everyone to ask. And let me tell you, it sent some serious shockwaves through the worlds of math, computer science, and yeah, even national security. To really get it, we have to start with how our digital world is protected in the first place. So before we can talk about the key, we've got to understand the lock. I'm talking about the metaphorical lock that guards pretty much everything you and I do online. Okay, so this system is basically the bedrock of all modern digital security. It's called public key cryptography. And the real genius behind it is this weird imbalance. It's built on math problems that are super easy to do one way, but just ridiculously, almost impossibly hard to do in reverse. The best way to think about it is like a really special kind of padlock. See, anyone can just walk up and snap it shut. That's the easy part. But opening it, nope, you need the one specific key. Trying to pick that lock without the key, well, that's the hard part. And for the computers we use every single day, it's pretty much impossible. So what is this mathematical lock exactly? Well, it boils down to this really simple contrast. On one side, you have the easy problem. Take two massive prime numbers and multiply them. Your laptop could do that in a blink. But the hard problem, that's taking the gigantic number that comes out of that multiplication and trying to work backward to figure out the original two primes you started with. That's called factoring, and that hard problem is literally what our entire digital security is built on. And, for decades, we've all been pretty comfortable with this. Our entire digital life has been built on the fact that for the computers we have now, classical computers, that hard problem is, for all intents and purposes, unsolvable. And listen, this isn't just some vague assumption. It's the whole reason this paper exists. Shor himself points it out right at the beginning of his paper. He says, look, problems like factoring, they're generally considered hard on a classical computer. That's the whole foundation of our current security. So why is it so hard? What's the big deal? Well, a normal computer, it has no choice but to use brute force. It's like that burglar we talked about, literally trying every single possible key combination, one by one by one. And when you're dealing with the massive numbers used in modern encryption, that process would take, and this is not an exaggeration, billions of years, longer than the universe has been around. So it sounds like our secrets are safe forever, right? The locks are just unbreakable. But what if you didn't have to play by those rules? What if there was a totally different way to compute? A new kind of machine that could somehow skip the one-by-one part. And this is where things get really wild. See, this idea wasn't totally new. Physicists, people like the brilliant Richard Feynman, they'd already been thinking about this stuff. They were wondering, hey, to simulate the weird, wacky world of quantum mechanics, don't you kind of need a computer that runs on quantum rules? It was this wild, mind-bending idea, and it led to an even bigger question. Okay, if we built one, what else could it do? And that is where we get to the main event. Because in 1994, Peter Shor came along with the answer. He published this blueprint, this algorithm, that basically drew a straight line from the weird theory of quantum computing directly to the very real problem of breaking our digital locks. And this is it, the paper itself, Algorithms for Quantum Computation, Discrete Logarithms, and Factoring. It looks so unassuming, doesn't it? But inside this document, Shor laid out step by step exactly how a quantum computer could just shatter those hard problems. I mean, just blow them away with incredible speed. It was and is a total theoretical masterpiece. Okay, so how on earth does it work? Let's go back to our lockpicking burglar. Remember how the classical computer had to try every key one by one? Well, imagine if our burglar could try all the keys at the exact same time. That's kind of the mind-bending idea behind a quantum principle called superposition. But here's the really brilliant part. Just trying them all at once isn't enough. The real magic of Shor's algorithm is that it then uses a kind of special mathematical lens to look at all those possibilities at once and find a hidden pattern, a specific rhythm in the chaos. And that pattern, it isn't random. It points directly to the right key. It reveals the prime factors. It doesn't guess. It just knows. It finds the secret structure of the lock. You can imagine the implications of this were huge and immediate. Shor's paper wasn't just some neat solution to a math problem. No, it created an entirely new field of study. And, let's be honest, it posed a direct existential threat to, well, pretty much all of global security. I mean, listen to this line from the paper's introduction. It is so simple and so chilling. We thus give the first examples of quantum cryptanalysis. That's it. With that one sentence, Shor basically announced the beginning of a whole new era. For the very first time, someone had laid out a real, credible, mathematical roadmap for breaking the encryption that held our entire digital world together. And just so we're clear, what's at stake here is not some abstract academic idea. We're talking about your bank account, your emails. We're talking about secure government communications, the things that verify your identity online. I mean, it's the entire scaffolding of trust that makes the modern internet work at all. So, you see, Shor's paper wasn't the end of the story. Far from it. It was the starting pistol for a massive technological race. A race that is still going on and getting more intense every single day. Yeah, this timeline really puts it all into perspective, doesn't it? Think about it. The digital locks we rely on, they were invented way back in the late 70s. The theoretical key to pick those locks, that was designed in 1994. And now, well, now we're in the home stretch. The big push is on to actually build a machine that's powerful enough to turn that theoretical key into a real one. But here's the really fascinating twist in all this. Shor's paper didn't just start one race, the race to build a code-breaking machine. It actually started a second, parallel race, a frantic global scramble to do the complete opposite, to invent entirely new kinds of encryption. We're talking about new digital locks based on totally different math problems, problems that, hopefully, even a huge quantum computer couldn't solve. And that leaves us right here, with the ultimate cliffhanger. It's this incredible race between two frontiers of technology, and both of them were kicked into high gear by that one single paper from decades ago. So the question is, what gets built first? The quantum key that can unlock everything? Or a new kind of lock that the key can't open? The answer to that, well, it's going to define the future for all of us.